Hello. Good. Good morning, everyone. So, statistical methods, and we are talking about random field theory-based p-value correction. And we had a bit of a break, so 1 week. So let's first discuss what we were discussing and what we will do then today. So we've been talking a lot about random fields, and the reason why we're talking about random fields is because we want to use them to do some sort of multiple testing p-value correction. And what we are concerned with all the time currently is to actually first describe a random field. So here I now give some examples for a random field over the real line. We are interested primarily in random fields over 3-dimensional space, but to visualize it's easier to do it on the real line. And we now have some language available to describe a concept from which we can sample, and then we get realization of random fields which might look like this or like this. Yeah. So these are our random fields, and we denoted them by something like this. And we said these are random variables, but they are a function of the small x, and the small x is a point in space, and this d can be one-dimensional, like here, 2 or 3-dimensional, and 5 it's 3-dimensional. And we have a language, and we also looked at how we can simulate these if we concern ourselves specifically with Gaussian random fields, so where all the finite dimensional distributions are Gaussian, because then we can evaluate the expectation parameter and the covariance matrix based on some form, and then we can put it into a multivariate Gaussian random number generator, and then we can obtain such realizations. And we looked at those things in 2D and looked at some visualizations, and we figured also that the covariance functions is the crucial thing. So that was basically establishing random fields and Gaussian random fields. And then the last that we discussed was actually a measure of smoothness. So we were interested in smoothness, and the motivation for that was that if we are interested in probabilistic properties of excursion sets, where excursion sets, again, maybe let's briefly rehearse that. Also, an excursion set was a subset of the domain of the random field, which we also call the search space, for which the values of the random variable are equal or larger than some value u. So if we want to study the probabilistic properties of such excursion sets, so remember again that if we have a realization of a random process, something like this, and we have cluster forming threshold, or just a threshold or a level, so there are many words for the same thing, then the excursion set refers to the points in the search space, so these points here, for which the random field takes values larger than this value u. If we want to study the probabilistic properties of such excursion sets, then one thing that is helpful, and which was introduced in 1991 by Carl Friston in the context of FMI, is to study the smoothness of random fields. And so, for example, if we have something very smooth, then and everything with an expectation function about 0, then the probability for this excursion set to be large is relatively small. And if we have something that is very rough, so something like this, then it might be larger, but also the specific components smaller that form part of the excursion set. So to study smoothness then, last time we discussed this principal measure of smoothness, which we called sigma. So that's this sigma variant. And we defined it as an integral over the d-dimensional unit, square or cuboid or interval of the determinant of the variance matrix of the gradient of the random field to the power of minus 1/2, minus because what is actually measured here is the roughness. So the stronger the gradients, the stronger, or the larger the gradients, the larger the roughness, and then if we take to the power of minus 1/2, then we get a smoothness measure, and that integrated over the unit square. And then we looked at a couple of examples for that. Specifically, we looked at the case that we are actually dealing with the one-dimensional case, so d = 1. And then we discussed that if we have a Gaussian covariance function, which for a Gaussian random field, which has this parameter L that we also looked at previously, then one can show that this smoothness measure evaluates to this length parameter of the Gaussian covariance function for a Gaussian random field. And that can be shown relatively straightforwardly with a little belief in total differentials. So that's this proof 4.5. Has anyone looked at this proof? No? Good. So again, to really capture what this smoothness measure means, it's fairly simple. So we always assume that our expectation function for the random field is 0, and then the smoothness measure, so this sigma over the interval, let's now keep that really at this interval, so from 0 to 1. If we have something like this, let's say this is 0, then here the sigma is not the greatest. This sigma would be something like, so I'm just making this up, but you get the idea, 0.2, sorry, it's actually high smoothness, so this would be something like 20. And then if we have something like this, then the sigma would be something like 0.2. Yeah, so it's just a number that describes how smooth the random field is. And of course, these two lines here, the blue line and the pink line, they are realizations from this random field, but you can imagine taking more and more realization and then looking at the smoothness of every one, so visually, and this measure of smoothness, because it involves the variance, captures this captures this stochastic probabilities of the random field. Yeah, questions about this? So that's really just a measure of smoothness. It's one has to go a little bit like we did last time, go in detail about what that means, and then one can try to analytically evaluate this for random fields that one has analytical descriptions of. Now maybe make a little jump to the real world. So in the real world, of course, we can only approximate the gradient here by computing finite differences of some realization of a random field, and we of course can only estimate the variance using a variance estimator. So this measure of smoothness is actually evaluated by SPM, but of course for a discrete random field, and not using analytical gradients, but using numerical gradients, and of course not using analytical variances, but variance estimation, and then of course not using an integral, but using a sum. But this measure in its real life form, meaning in a numerical approximate fashion, is evaluated by SPM in the famous function SPM est smoothness. And we will come to that and on what kind of data it actually works when we discuss how the whole framework that we've been discussing is actually applied to fMRI data, which is of course discrete and finite and everything. Good. So we have now these theoretical entities, random fields, and we have a measure of smoothness, which we can apply to these theoretical entities. And in principle, we could now go and, using this measure of smoothness, discuss certain probabilistic properties of the excursion set. So, for example, what the probability that for example, the maximum of a random field is larger than some level, or that the excursion set, equivalently the excursion set includes at least 1 point at a given level. So in principle we could do that, but the measure of smoothness that is used in fMRI data analysis, which you find in the papers and which you also find in the software. You find this measure in the software, but you also find this other measure in the software, uses a reparameterization. And this is the first thing that we want to discuss today. So the first thing is for today to discuss smoothness reparameterization. And for those familiar with fMRI data analysis, this corresponds to the fact that we hear about full width half maxima. So whenever you did a SPM course or whatever, you will have come across about of a full width half maxima, not only during smoothing, I hope, but also when you look, for example, at the SPM table, you find some full width half maxima in there, whatever that means. And the second part, so more for the second hour, then is what I call volumetrics, because we will also not only have to talk about how to measure smoothness, but also how to measure volumes. And this leads in effect to what neuroimaging people know under the term results. So if you ever did an SPM or whatever course, you will have come across results. No? Where did you do your SPM course?
Hamburg.
In Hamburg. And you didn't talk about results. You forgot. You never heard of results. So have you ever listened to or have you attended an SPM course, or have you ever looked at your table in SPM? Because in the of course, but in the there's a footer in the table, and if you look at the footer in the table, there these things come up. So I can show you maybe. I managed to do that by clicking here. No, I don't manage to because I don't have my project work on here. We have it in there? I don't think so. I don't know, none of this will work because I just don't have it on here. Does the SPM? No, no. So believe me, it's in the SPM table, and we will see that. And I showed you that in the very beginning of the course. Actually, there's in the footer of the SPM table there you find both the terms full width, half maximum, and result or result volume. So yeah, have a look. Good.
You have the FE10.
Yeah, that's the full width, half maximum.
Yeah.
Oh yeah, reasons.
Reasons, yeah. Volume. Yeah.
Okay, so we have now confirmed that actually in the SPM table the terms full width, half maximum, and results are there. Good. So it all makes sense what I'm talking about. Good. So then the first thing is smoothness reparameterization. So let's go. Smoothness, I'll just write it up again. So in principle, as I said, our measure for smoothness is perfectly fine, so we wouldn't have to do anything. But Friston et al. 1991 and then Worsley et al. 1992 decided to use this reparameterization. And what I mean by reparameterization is simply that instead of capturing smoothness in terms of this sigma parameter, it's captured in terms of the following. If we talk about the three-dimensional case, and we will only talk for smoothness reparameterization about the three-dimensional case because it's in the application to fMRI. So it is expressed as the following. So this is a number here. So the sigma is the smoothness that one can compute from a random field, so something like 10. And this is now re-expressed in terms of this constant factor. That's not so much of a problem. So that's just 4 ln2 to the power of minus 3/2. But then 3 different numbers. So something, if I don't know, what is this 4 ln to the power of minus 3/2? How much is that? Can you type that into, what's it, active participation part? What's
log to the power of 3/2, which is not really helpful, I guess.
4 log to the power minus 3/2 0.216.
Something? You agree?
I think so. Yeah, I just get a simplification of that.
All right. So this is just a constant, obviously. So let's say we have here 21. So if we multiply this by 100, so if the product of these three numbers is 100, then we get our 21 back. Now, the problem with this reparameterization is that, of course, there are many ways that you can create a 100 by multiplying three numbers. So, for example, you could have 25 times 4 times 1, or you could have 1 times 100 times 1, or you could have 2 times 50 times 1, or whatever. So instead of expressing smoothness with a single number, you express smoothness now with a product of three numbers, which is not really desirable, but this is how things are in the imaging world. Now the question is, of course, where does this come from?
Yes, yeah.
So the question is, of course, why express what is this whole thing about? Where does it come from? And that's actually not that easy to explain. And from the math that is in the script right now, at least I'm convinced that this holds if one looks at diagonal elements of a Gaussian convolution kernel that I will tell you in a second about. I'm not quite sure whether it also holds for the off-diagonal elements. For this, I want to do some, or I have to do some spectral representation of Gaussian convolution functions and of random fields. But I didn't really want to put this into the script, and I haven't done that yet because it involves complex numbers, and I want to save the poor psychologists from complex numbers, because that would open a whole other field of problems. So I can tell you roughly where this is coming from, but not in all detail, because I'm myself not fully convinced that it holds in all detail. It might, but I'm not fully convinced yet, because where this is coming from is, of course, not documented in the brain imaging literature or the attached literature. So what's the general idea where this is coming from, and what are these full width half maxima? So the general idea of where this is coming from is the following. So assume that you have, maybe let's do it in a two-dimensional case. You have a random field. Let's say this is a realization, something like this, and we've seen things like this before, that is of a certain smoothness. So you could now go and evaluate our little formula, which, let's see whether I can produce it without looking somewhere. So you could basically, on this random field which is defined, you could go and evaluate this formula. I think that's roughly it. Now, that's fine. You could also do something else. You could imagine a white noise random field where the probability of the white noise random field, or white noise Gaussian random field to be precise. I will show you a re-realization in a second, but it roughly looks like this. derived from the fact, so white noise Gaussian random field is defined in terms of the covariance function, which is, let's look that I write the covariance function correctly, in line with what I always write here. I think I just call it C. Yeah. Let's do it in blue. The covariance function of a white noise random field is as follows. Oops, it's it's sigma square, so some variance parameter for x being y, and it's 0 for x not being y. This means that all of the random variables which sit at all these locations in the random field are independent. Yeah, so you can simply, if you like computers, you can imagine using the rand_n function in MATLAB and sample many, maybe 100 times 100 independent, normally distributed, zero-centered random variables with variance parameter sigma square. And if you, of course, increase the variance parameter, all of the variables will have a larger variance. So let me show you how that looks here, because we have that. So this one here, I don't do anything right now. This one here, where it says Dirac, which just means that it's in this case 1 if it's x equals y. This is a white noise random field realization. Yeah? Now, that's only part of the thought experiment here. Now assume that, what kind of color? Let's use this. Now assume that this is smoothed with a in this case, two-dimensional Gaussian kernel. Yeah, so we are looking at a two-dimensional white noise random field, and we now think about smoothing this or convolving this. That's the same thing with a Gaussian kernel. So that's just a Gaussian here, a bit funky. With a Gaussian kernel, so basically putting, so what happens there is, of course, that you put the Gaussian kernel here, sum up all the things according to the weights that are given by the Gaussian, and then you move the kernel one step further so that you smooth the field. And by doing so, you can, depending on the width of the smoothing kernel, you can create a smooth random field. So this is also how before the advent of proper random number generators, you could create, of course, on a computer random fields with a certain smoothness. So you just sampled independent random, normally distributed random variable, and then you used a smoothing algorithm like you smooth brain images, but here's smoothing simulated data to get a smoother field. Yeah, does that make sense? Smoothing. So you smooth something that is fairly non-smooth. And then you can recreate, or the idea is that you can recreate a field or a realization of a field that has the same smoothness as the original field. And now the crucial parameter that plays a role here is the the kernel width. So this is a Gaussian. It's not a probability density function, but it's a smoothing kernel. The kernel width of this smoothing kernel. Yeah. So if you make it very broad, then you can create something very smooth. If you make it very small, you can create something less smooth. Yeah. So here there are now parameters. So for example, for a 2D thing, there's a parameter matrix. Let's call that x1. I will make it more explicit in a second. So let's call that just sigma 1 1, sigma 1 2, sigma 2 1, and sigma 2 2. There's a parameter matrix that you can adjust so to create this kind of smoothness. Yeah. And then you can say, okay, the smoothness of this real random field that I'm looking at is as if I convolved a white noise Gaussian random field with a smoothing kernel of this and this width. And then instead of expressing smoothness in this way, you can say, okay, the smoothness of this random field is like the kernel width of my Gaussian. And this is essentially this. We will go into more details in a second. Yeah, so that's the general idea. Personally, I think it's horrible because it makes the whole thing more complex than necessary. And also if you look into the software estimates, so the SPM smoothness estimates smoothness, not in terms of somehow adjust. So, I mean, what it could do is, I don't know, something like simulating white noise, smoothing it, seeing what you get, compare that to somehow your real smoothness and figuring, okay, it's not smooth enough, then simulating some noise again, smoothing again, and so on. That's not what the software does. The software calculates this. But the language and also the calculation, or let's say the estimation and approximation of this, is then transferred into this smoothness parameters in terms of this hypothetical Gaussian kernel. These numbers, so the full width half maximum, they will play an important role also again in terms of measuring volumes and the concept of results. So this is why the software does that. But 20 years or more have gone by, so in principle it could do something else, but we will see that later. So that's for the moment. Let's now deal a little bit more with this idea of full width half maxima. Yeah, so the next thing that I want to introduce is full width half maximum for a Gaussian kernel. So we will do this for the univariate Gaussian, because that's most intuitive, and the generalization to independent, isotropic higher dimensional kernels is fairly straightforward. So what is meant by this full width half maximum and what's going on? So you all know how the Gaussian looks. No, doesn't really look like this. Something like this. And then it has a mean or an expectation parameter, that's sigma square. And what's the other parameter of a Gaussian? The variance. And what does the variance describe?
Like
how much the spread is there. And then you know from psychology statistics, you know something about 63% are within 1 standard deviation or something, right? So you know that, let's say these are kind of the 63% that is always then discussed in psychology, undergraduate statistics. So 63% of the cases that can be sampled from a univariate Gaussian are within 1 standard deviation. Yeah, and then you know that 2 standard deviations are these 95%, and so on. So that means to describe the width of a Gaussian, you have a perfectly fine parameter, which is called the variance. And if you take the square root of the variance, you have the standard deviation. So the width of a Gaussian is already specified by a variance. But of course, you can also re-express this as it's done for the full width half maximum. So first of all, what is the full width half maximum? This refers if you have any function for which we assume that there is a maximum at 0. So if we assume that if you have a function f and it has its maximum at 0, then the full width half maximum is the distance between two values x1 and x2, and at these values x1 and x2 the function has fallen off to half of its maximum value. What this means is the following. If well, maybe let's try it here. So here you have a distance, not a distance, here you have the maximum. So here at f0 you have the maximum of f. Yeah, so here there's the maximum. And then you can ask yourself, okay, where at one point, how far do I have to go out into this direction and into this direction to go to the place where I'm at f0 half. Yeah, so you can see that f0, so in this case at the expectation of the Gaussian, you have this distance, a half of this is roughly here, and then you can go in this direction, so to the left and to the right, and you end up here and here, and then you can look at these values x1 and x2 that I describe here, and you can look at the distance between those, and that's the full width at half maximum. Yeah, that is something that is interesting in signal processing. I find it's a little bit of a funky quantity because yeah, that works nicely, and we can do that analytically to get an expression for the Gaussian, but it really seems to be tailored to functions that have a unique maximum and are symmetric about this maximum, because I mean, what is the full width half maximum of something like, I don't know, it's maybe not that, something like this. So what is the full width half maximum here? I mean, you have an asymmetric thing then, and it's, I don't know. So for me, this full width half maximum makes a lot of sense, and this is where you always find it for the Gaussian, but I'm not sure whether it makes so much sense for everything else. But nevertheless, the full width half maximum of a Gaussian can be analytically determined, and it falls out as the following equation. So I call it f. So don't confuse it with the function here. I just call it f because I didn't want to write FHWM all the time. the full width half maximum of a univariate Gaussian evaluates to square root of 8 ln 2 times the standard deviation of the Gaussian. Which means the full width half maximum of a Gaussian is just a scalar multiple of the variance parameter of the Gaussian, which makes a lot of sense because the variance describes fully how wide a Gaussian is, and so does the standard deviation. And the full width half maximum now doesn't add any other information in terms of the width. It just expresses it as using a scalar multiple. So how much time do we have? Yeah, we have 5 minutes, so I think in 5 minutes I can briefly sketch how one can compute it. So this is now this proof 4.25, which actually just calculates this formula for a Gaussian convolution kernel. So it starts with, so I'm going briefly over it, so you should study that yourself and verify it for yourself. So it starts with that the full width half maximum is defined as the distance between these 2 points, x1 and x2, at which the maximum is has fallen off to 1/2. The function that we are actually looking at is, of course, the Gaussian. So, of course, we are applying this whole thing to the Gaussian, which, of course, you know, has this form. And we are now interested in finding a point. I think there's one h, so in 427 that shouldn't be h of x1 but g of x1. I think I changed nomenclature there to find two or denotations to find 2 points x1 and x2 for which we are at 1/2 of g x maximum, and x maximum for such a Gaussian is of course mu. And if we make the additional assumption that this is mu is 0, then of course we can then we have a closed form expression for the maximum. So what happens then in this proof is that we are looking for, we say, okay, we want to find this x for which we are at 1/2 of the maximum, and then one can plug in the different, actually we're not saying it's 0, sorry. We just say that the maximum is at mu. This is the thing that we know. We know for Gaussian the maximum is at mu. It doesn't need to be at 0. It can be anywhere. There I was mistaken. So we start from this, and then we plug in this function and also this function, but for xn, which then will be mu. And we are led essentially to, after some reformulation, to the equality 2ln 2 sigma square. And then we make the additional assumption that mu equals 0. And then we are led to x square 2 ln sigma square, and then of course we get two values, x1 and x2, which are given by plus minus square root 2 ln what's the 2 missing, 2 ln 2 sigma, where we already took the square root of sigma square. And then, so these are our points now. So we have one point x1 and one point x2, and we assume they are symmetric about 0. So one is the negative one is the positive one. So the distance between them is then just 2 times this value, which means that our fx x1 minus x2 is 2 square root 2 ln2 sigma, this is then, if you think of 2 as square root of 4, then you can put the 4 in, then you get 8 there. This is then 8 ln2 sigma. So this proof it's not very interesting. It's just showing how one can, by using the definition of the full width half maximum, derive the fact that the full width half maximum of a univariate Gaussian corresponds to a scalar multiple of its standard deviation, or the square root of its variance. Yeah, it's just a little calculation which assumes a lot of things, like the symmetry of the whole thing, that one looks at mu 0. It gives you a little bit of an idea. If you have another symmetric function, for example, you could have a function that looks like this. So like a triangle function. It gives you a little bit of an idea how you would be able to compute the full width half maximum of that if you ever need to. But beyond that, it's not that instructive. Okay, so now, now we have done the full width half maximum for a Gaussian. Yeah, maybe let me finish this smoothness reparameterization bit by saying a little bit of what one actually has to do to derive this. So in principle, to show that no, we are not quite there yet, sorry. Let's have a break now, and then I tell you where this thing is coming from, and then I tell you what one have to do to actually show that. So, but let's have a break first until 9:05.